Example 2. Okay, this example is more difficult than example 1 since it involves two loading. Okay, this joint is subjected to a force F and P to determine the state of stress at points A and B. Okay, the member has a rectangular cross-section area of width 50 and thickness of 20. And in this sketch, you can see that the dimensions A equals 48 centimeter and B 8 centimeter. So the P and F are 302 and 120 Newton, respectively. Okay. So first of all, let's look at this one. Let's set a coordinate system first of all. Okay, we will have the x direction, y direction, and z direction. The z direction is just perpendicular to the xy plane. Okay, with these coordinates, then we can sketch the cross section too. Okay, let's draw the cross section here. This is the cross section. The cross section will be on the xz plane, right? You have the x direction, z direction. Okay. The dimension here will be dimension here it's a thickness, right? The t. The thickness will be 20. And here, the dimension, the width equals 50 millimeter. Okay, and our point A is right on the edge here. This is the point A, and the point B is on this corner. Okay, and let's look at this thing. This is the combined loading, and so we have two forces F and P. Okay, the F is here and the P is here. Okay, our first step will be what the steps said. The first step is moving the forces to the cut section. Right? We will just analyze the internal forces at the cut section. Okay, so this is our first step. We'll analyze internal forces. Since here will involve two external loadings, it will be more complicated. So normally we recommend to use a table. I recommend to use a table to do this analysis. Okay. We draw the table in this way. So the potential internal forces will include normal force. So the normal force is along the axial direction. And the axial direction in this case is y direction, right? So we can say this normal force Fy along the y direction. And you can also have shear force in x direction. Let's call it Vx in x direction. And bending moment, right? You may have three types of internal forces. And you have two external loadings. P 300 Newton, F 120 Newton. Okay, let's examine them one by one. Do you think the P will generate axial force along y direction? P is here. Okay, you can directly move it to the local to the centroid P. Right, this is parallel to the y-axis. Right, so you will have this P will generate a normal force P. Will the P generate any shear force at the cross section? No, right? No shear force. Will it generate a bending moment? Of course, right? It had a distance to the y-axis B. Right, this is the arm. So the bending moment here will be PB. Then let's look at F. Do you think F will generate any normal force? No, right? It's perpendicular to y, right? So here is no. Will it generate shear force on the cut section? Yes, right? It equals F. So how about bending moment? The F is here. It has a distance to the cut section. That is A. That is the arm. So the magnitude will be F times A. Okay. So let's summarize them. Summarize this. The effects of different loadings and to get the resultant effective internal forces. Okay, the Fy has only one component, that is P, right? You get a 300 Newton. And the Vx has one component, that is F, 120. And the M has two components. Can you simply add them together? Okay, before do that, we need to confirm one thing. We need to confirm, do these two bending moments have the same sign? Okay. Look at the PB first. Okay, the P is here, B is here, so the direction of the PB will be in this way, right? And the FA, F is pointing left, A is here, so the resultant bending moment will be in a opposite direction. So they will have different signs, opposite signs, right? So we need to add a negative sign to the first one, so that the resultant bending moment will be negative 300 times B 80. This is 8 centimeter, it will be 80 millimeter, right? Plus 120 times 480. Okay, the results will be 33,600. Okay, so after this, we can calculate the normal stresses and the shear stresses at point A and B, respectively, okay, separately. Then step 2, we will look at the normal stresses due to the axial force. Due to the axial force. Then here it says this is due to axial force, and we normally assume that the normal stress is generated by axial force is uniformly distributed on the cross section. So that means sigma A equals sigma B. Right? The normal stresses at point A and B have the same value, that is Fy over A. Right? The Fy, the 300, the A is just 50 times 20. Right? So you got 0.3 MPa. Is this positive or negative? Now look at the direction of P. Okay, it will stretch it, so it will be in tension. This is a positive. Okay, positive 0.3 MPa. Then do you have other normal stress components? Yes, right. So the shear force will not generate any normal stress, but the bending moment will generate normal stress. Right. So we will analyze normal stress due to the M. Okay, at a point A, A is here. You can see that the point A is right on axis, the z-axis, right? Meaning that since the bending moment is with respect to z-axis, okay, so this is the centroid. The bending moment will be respect to the z-axis, A is right on this axis, meaning that the YA equals what? YA equals 0, right? So the sigma A equals 0. Now how about sigma B? Sigma B, we need to calculate it by using the equation MYB over I. Right? The M is 33,600, and YB is half of the thickness, right? Half of the thickness of 20 over 2 over I. So what is the Y? What is the I value, the moment of inertia? I equals, this is BH cubed over 12, but here just which value is B, which value is H, right? Since this is the M is with respect to Z axis, so the bottom will be the 50, right? Will be the 50. So you will have 50 times 20 cube over 12. Okay, you'll get 33,300. Therefore, you get the value here. Just substitute in 33,300. So you will have 10.1 MPa. Is this compressive or tensile? Is this negative or positive? Right, just compare these two bending moment. Right, look at here. In the two bending moment, the blue one is smaller, the red one is larger. So the resultant bending moment is along the red direction. That means at the left-hand side, at point B, it will be in compression. Right, so this means the calculated value 10.1 will have a negative sign. Okay. So this is the sigma B. Okay. We're done with analysis of normal stresses. Right? This normal stress can be due to the axial force, can be due to the bending moment, but there's no other things. The shear force will not make any normal stress. So we're done with the normal stress analysis. What will be the result of the Vx? The Vx, will it generate shear stress? Of course, it will generate shear stress. So we need to analyze the shear stress. This is the step 4. Shear stress. So let's look at point A first. To calculate shear stress, the equation we will use will be tau equals VQ over IT. Right? So at point A, the V has been there. We have just Vx, right? And I has been calculated. So what is the T? Right? What is the T? What is the Q? Okay, so those are the two things you need to determine. Right? So what is the QA? What is the TA? Right, you need to determine these two things so that you can get the correct result. And let's draw the cross section again here. This is the Z direction, and your Vx is in this direction, right? The point A is here, right? So to analyze this, to calculate the tau A, you need to cut the area first, right? Cut the area from here. You got this area, right? The local centroid is here, global centroid is here. So the distance is D, right? So our QA will be AA times DA, right? The A, the area, the blue shadow area, will be just look at the dimension here. It would be 50 times half of the thickness, right? This is 10. This is the area. And the D will be half of the thickness, or that will be 5, right? So here you will get 2,500. And the TA, I recall our theories when we derive this equation, when we derive the tau equals VQ over IT. So what is the TA here? The TA here, will that be the T value 20 or the W value 50? Okay. So recall the definition of this thickness. So you will know, you will realize that the TA equals 50 here. Okay, 50 millimeter. Okay, now so we can calculate the tau A. That is VQ over IT, right? The V is 120, Q 2,500, I is 33,300, and the T is 50. Okay, so here we get 0.18 MPa. Okay, so it's important. This one is important. Okay, to identify the correct T for this equation. Okay, then this is the shear stress at point A. So how about TB? B is right here, right? If you cut a area through point B, what do you get? You get a 0, right? So A, B equals 0. Means what? Means QB will be 0. So VQ over IT will be 0. Okay? So the tau B will be 0. You get nothing. Have no shear stress here. Now we're done with calculations of all components. So the last step, you just need to summarize them together. Right? This is your in-class work. Right? Do not remember summarize them on a paper and then substitute it to Canvas. I will leave a assignment there. Okay. So this is your ICA. So submit it to Canvas. Okay. To summarize our results. Okay. Look at here. This what do you need to summarize? You need to summarize sigma A, sigma B, tau A, and tau B. Okay. Look at sigma A. You have two components. Right. The first component is here. Second component is 0. Just put them together. And sigma B, first component is here. Second component is here. Okay. You just combine them together. And tau A, tau B, you have just one value. Okay. Okay. Summarize them by yourself, and do not forget submit it to Canvas.